Hi friends, welcome back to Wikipedia World. Last lecture we introduced you to resistance, factors affecting resistance and Ohm's law. Today we'll start off by discussing what are ohmic and non-ohmic resistance. Then we'll briefly discuss what is semiconductor. After that we'll dive into resistivity. We'll understand what resistivity or specific resistance is, and we'll also see what conductivity is. So let's kick off with ohmic and non-ohmic resistance. The previous lecture we finished off by discussing Ohm's law. To recap, Ohm's law was V is equal to I times R, and in the form of a plot, what that meant was that if I plotted I and V, then I would get a straight line like this with a slope of R, which is constant throughout. Since this is a straight line, whether we measure R the slope here or we measure R the slope here, they would be the same. Okay, so this was representation of Ohm's law. Now there are materials which follows Ohm's law, which follows this nature of the VI plot. Those material are known as ohmic resistor. Those resistors are called ohmic resistor. Ohmic resistor. So what are ohmic resistor? Ohmic resistor are resistors which follow Ohm's law. And what that means is that V versus I plot is a linear plot. The resistance is same at any condition of potential and current. And what are those materials? Normally our metallic conductors are ohmic resistors. For example, copper, aluminium, silver, such materials. Now since the ohmic resistor follow this linear relationship, it is quite obvious that the non-ohmic resistor will not follow Ohm's law, right? So if we were to draw the VI characteristic of a non-ohmic resistor, it would deviate from the linearity. For example, it might be something like this. Okay, so this is an example of non-ohmic resistor. What is special about this? The speciality is that it is non-linear. It does not follow Ohm's law, because Ohm's law confirms linearity. Here we do not have linearity. As a result, the resistance basically depends where we are measuring, at what current we are and at what voltage we are. Suppose we are at this position, then the resistance under that situation will be given by the tangent at that position. So this will be the resistance here. If we were to measure the resistance over here, then we would get a tangent here at that point, and that would mean a resistance of this much. We can clearly see that this R2 is far more than this R1. Okay, and since there is a continuous change in resistance, obviously it is not following the Ohm's law. And this changing resistance with changing current and potential is known as dynamic resistance. It is dynamic in the sense that it is continuously changing depending on where we are. Fine. So this gives you an idea about ohmic and non-ohmic resistance. Particularly this plot is from a non-ohmic resistance known as junction diode. Some other examples of non-ohmic resistance would be transistors, would be diode valves, or filament of a bulb. Why filament of a bulb? If you think about it, the filament of a bulb is continuously heating up, and as we know that temperature with change in temperature the resistance change, and therefore the Ohm's law will no longer be valid. Fine. Now we know what is ohmic and non-ohmic resistor. Next, let's see what is a superconductor. Superconductor. Till now what we have seen is that all materials offer resistance to the flow of electron. But there are certain materials which offer zero resistance to flow of electron. Zero resistance. Okay? Experimentally it has been found. But the catch is that the conditions under which superconductor can be obtained is normally very, very low temperature. So a material normally becomes superconductor at very low temperature. I will show you some examples under which a material becomes superconductor. An example would be mercury, Hg below 4.2 Kelvin. That is very close to the absolute zero temperature, right? Or lead below 7.25 Kelvin. So these are examples of superconductor. You can see that the temperature at which superconductivity will occur is very low. Now come to think of it, superconductor is a very cool phenomena, as in there is no resistance. What does that mean? That means that if a current starts flowing, it will not require any potential difference to drive the flow, because there is no resistance to obstruct the flow, right? Therefore, superconductor are fields of active research, because if it were possible to bring superconductivity at room temperature, what we can do is potentially we can use those materials to conduct electricity through long distance without any loss of energy. Resistance results in loss of energy. So absence of resistance will restrict that loss of energy. We can develop computers which are very, very powerful and very, very tiny. So these are some this is just the surface of what superconductivity can be used to. Therefore, it's a field of very active research, and maybe in the future you can be a part in developing a very good superconductor at room temperature. Okay, so with this short introduction to superconductor, let us jump into specific resistance or resistivity of a material. Specific resistance or resistivity. The name sounds that it has to do something with resistance. Let's see what it has to do with resistance. We have seen that resistance is proportional to the length of the conductor. Also, we have seen resistance is inversely proportional to the area of cross section of the conductor. Okay, now if we combine these two things, we get that resistance is proportional to L upon A, and if A is a circular wire with a radius R, then we can say resistance is proportional to length upon pi R square, isn't it? But what we see is still the resistance is not directly equal to. So we can replace this proportionality with equal to by introducing a proportionality constant, and that proportionality constant is known as specific resistance or resistivity. Let's introduce the proportionality constant. R is equal to, I will use this convention, rho This is our specific resistance. I will introduce it in details. L, length upon area. This is my resistivity. Okay, so the proportionality constant, which equates resistance with length of the conductor and the area of cross section of the conductor, is known as resistivity. So formally we can define resistivity as the resistance offered by a wire of unit length and unit area of cross section, isn't it? If we replace L as 1 and A as 1, then R becomes exactly equal to rho. Therefore resistance is equal to resistivity for unit length wire of cross sectional area 1. Fine. Next, let's see what this means. This means that if we were to increase the length by twice, then resistance would increase by 2. Since rho is a material property, it is independent of the dimensions, right? Resistivity is a material property. We'll see what factors this resistivity depend on. It is not just a material property, it also depends on the temperature, but it is independent of the shape. So this proportionality constant can be used to correlate resistance with length, area or dimension of the wire in general. Let us see the units of resistivity. We can write resistivity rho as resistance times area upon length, right? We just cross multiplied it. Now if we extract the units from here, resistance is ohm, area SI unit is meter square meters, and length is meter. So resistivity can be written as ohm meter, right, or ohm meter. So this is the unit of resistivity. Now what does resistivity mean? Resistivity means the higher the resistivity of a body, higher will be the resistance for the same shape. Therefore bodies which are conductors will have low resistivity. Bodies which are insulator will have very high resistivity. Just to give you an example, silver is one of the most conductive materials. Okay, so rho silver Ag is 1.63 into 10 power minus 8 ohm meter, whereas insulator, wood is, or glass is insulator, its resistivity is of the order of 10 to the power 10 to 10 to the power 14 ohm meter. You can see that this is minus 8, so small, and this is power 10 or 14, so large. So resistivity is basically the notation that will decide whether a material is an insulator or a semiconductor or a conductor. With this introduction, let's see what are the factors on which resistivity depends. Factors. One is the material. Obviously, as we have seen, depending on the material, the resistivity will vary. Okay, and it can be 20 orders of magnitude different depending on what material it is. Minus 8, 14, so different. Second is temperature. Now the temperature factor is interesting, as in for a conductor with increasing temperature, resistivity increases. As therefore, with increasing temperature, the resistance will also increase. For a semiconductor, on the other hand, with increasing temperature, resistivity decreases. We will not go into the physics of it, but you should know that for semiconductor, the temperature property of resistivity is opposite to that of a conductor. And for alloys, most of the alloys, temperature does not affect, does not change role. Fine. So we have seen the material property, we have seen the temperature property. Now let's touch upon another concept which is parallel to resistance conductance. Here, since there is a resistivity, there ought to be a factor called conductivity. Conductivity. Basically, conductivity is the opposite of resistivity, and conductivity is denoted by a sigma is equal to 1 upon rho, opposite of resistivity. Fine. And if we calculate from here, 1 upon rho will be, rho we take here, L upon RA. So this is our conductivity. Units will be just opposite of resistivity, and that would be ohm meter whole inverse. Fine. Or in terms of Siemens, we can write ohm inverse is Siemens, so Siemens per meter, or men per meter. Fine. Now we have seen the different concepts connecting resistance, resistivity, conductivity, material properties that affect it, temperature, how does that affect it. Now depending on the application where we are going to apply the material, we choose the material. Like if we are going to do house wiring, we don't really want a material that will have high resistance that causes a lot of energy losses. We want a material with very low resistivity or high conductivity, like aluminium or silver or copper. But silver cannot be used for practical purposes, it being very costly, so normally copper is used. Then if we need something which should not be affected by temperature change, the resistivity should remain constant, then we will use such alloys. Namely, we can use manganese or constantan. These are materials whose resistivity does not change or changes very less. Then if we want something with high melting point and high resistance, for example, in the filament of a bulb, we want high resistance because it needs to heat up, energy needs to be lost to heat it up, therefore high resistance. And since it is heating up, it should not melt, so high melting point. One of the most important such material is tungsten, so we normally use tungsten in filament bulbs. So we see that depending on the application, we need to choose material based on its resistance, conductance, resistivity change based on temperature and such things. So this is application engineering. You use the properties to your advantage. Fine. So these I will close today's lecture at this note. The next lecture we will see numericals. We have discussed a lot of theory in last 3 classes. We will see numericals, and that will help us bring all these concepts together. So hope to see you in the next class. Have a great day. Bye.